So in the previous section, I showed you guys how to use the first and second derivative of a function to describe the shape of the graph and find the maxes and the mins. If we want to graph a function that is defined on an unbounded domain, so for example, polynomials are defined from minus infinity to positive infinity, we also need to know the end behavior of the graph. So we're going to use limits in this section on how to find the limit as x approaches plus or minus infinity to determine the end behavior of the graph. And that's going to apply to horizontal asymptotes as well. We have talked about this before in college algebra, but not in terms of limits. When we talked about end behavior in college algebra, we did that in terms of the leading coefficient and the sign. We did that in terms of the sign of the leading coefficient and the degree of the polynomial. And if you recall, if the leading coefficient of a polynomial was positive and the degree was even, we said that the arrows of the graph, when we draw them, are going to go up and to the left and up and to the right, meaning as x approaches positive infinity, the y value is going to grow unbounded, and as x approaches negative infinity, the y value is going to grow unbounded. Then we also said if the leading coefficient is negative and the degree is even, we said the arrows were going to go down and to the left and down and to the right, meaning as x approaches negative infinity, the value of the function was going to go down, unbounded, to negative infinity. And as x approaches positive infinity, the value of the function is going to go to negative infinity. Then if we had a leading coefficient that was positive, but the degree of the polynomial was odd, we had that one arrow was going to go down and to the left and the other arrow was going to go down and to the right, which means as x goes to negative infinity, y was going to go to negative infinity. And as x goes to positive infinity, y was going to go to positive infinity. And then the last situation we have with polynomials and end behavior is if the leading coefficient was negative and the degree was odd, then our arrows were going to get switched where one arrow was going to go up and to the left and the other arrow was going to go down and to the right, which means as x goes to negative infinity, y is going to go to positive infinity. And as x goes to positive infinity, y is going to go to negative infinity. Now in calculus, we can actually apply limits to come up with why this works. So before we just gave you the rule, if the leading coefficient was positive and the degree was even, this is what happened. And we just gave you that rule. Now we're going to apply limits and you can see why this works. We're also going to talk about horizontal asymptotes. So say I had a graph that looks like this, where I had, let's say, a horizontal asymptote at y is equal to 2. If I had a graph that looks something like this, then I could use limits to describe the end behavior. I could say as the limit as x approaches infinity of this function, the y value, what it's approaching, would be 2. Right? Because as I trace this graph going to positive infinity, I'm getting closer and closer to 2. Now on the other side, I can say as the limit as x approaches negative infinity of this function, I could say that the value of y approaches 2. And if I trace that, I can see what happens as x goes to negative infinity, the value of y gets closer and closer to that horizontal. So when you're computing a limit at infinity, the algebraic limit laws and the squeeze theorem apply to these as well. So we're going to find the limit, and these examples A, B, and C. We're going to find the limit as x approaches infinity and negative infinity for each of these functions so that we can determine the end behavior for these functions. So first, let's find the limit as x approaches positive infinity for the function 5 minus 2 over x squared. I'm going to break this up as the limit as x approaches infinity of 5 minus the limit as x approaches infinity of 2 over x squared. Now this one here is easy. The limit of a constant, whether it's as x approaches 2 or x approaches infinity, the limit of a constant is going to be the constant itself. So the limit as x approaches infinity of 5 is just going to be 5. Now the limit as x approaches infinity of 2 over x squared, as the denominator of a function gets bigger and bigger and it approaches infinity, the entire fraction gets smaller and smaller. So, for example, think about the sequence 1 over 1, 1 over 2, 1 over 3, 1 over 4, and you just keep going. So where you get to like 1 over 100, 1 over 1,000, 1 over 1,000,000, as that number in the denominator gets bigger and bigger and bigger, that whole fraction gets so small that the limit approaches 0. So the limit as x approaches infinity of 2 over x squared, when that denominator gets bigger and bigger, that limit's going to be 0. So my answer is going to be 5. Now, if I do the same thing, but with negative infinity, I'm going to take the limit as x approaches minus infinity of 5 minus the limit as x approaches negative infinity of 2 over x squared. The limit of 5 as x approaches negative infinity is still 5. Now the limit as x approaches negative infinity of 2 over x squared is going to be the same thing. If you're plugging in values that are really, really big, but negative, into that x, when you square it, it's going to be positive. So you're going to get 2 over positive numbers that are really, really, really big, which means that fraction is going to get super, super, super small, to the point where we can say the limit is 0. So we can say for this function that the limit as x approaches negative and positive infinity, that both directions we get 5. Now if you actually look at the graph of that function, if you graph it on your calculator, you're going to get a picture that looks something like this, and you can see that there's a horizontal asymptote on the graph at y equals 5. So if I trace this graph, approach positive infinity, I'm getting closer and closer to y equals 5, and as I trace this going to the left, I also approach the value y equals 5. So it doesn't matter which direction you're looking at for this graph, both limits are going to be 5, which is what gives you that horizontal asymptote at y equals 5. Now for part B, we're actually going to use the squeeze theorem. I want to take the limit as x approaches positive infinity of sine x over x. Now we're going to use the squeeze theorem here. If I take sine x over x and I squeeze it between the functions negative 1 over x and positive 1 over x, then if I take the limit of all 3 pieces here, and when I do that, I can see that the limit as x approaches infinity of negative 1 over x is 0. And I can see that the limit as x approaches infinity of 1 over x is also 0, which tells me if I take the limit as x goes to infinity of sine x over x, if that is greater than or equal to 0 but less than or equal to 0, then it has to be 0. So I can say that the limit as x approaches infinity of sine x over x is 0. I can make that same argument for the limit as x goes to negative infinity of sine x over x. I can make that same argument and say that as x approaches negative infinity, that's also 0. Now, when you look at the graph of sine x over x, you're going to get a picture that looks like this. I'll see if I can draw this nicely. It oscillates up and down over the x-axis in both directions. The height of those waves keeps getting smaller and smaller and smaller and smaller until it gets closer and closer to 0. Part C of this example, we're going to take the limit as x approaches infinity of the inverse tangent of x, and we're going to do the same thing for as x approaches negative infinity. So we know from trig class that the limit as x approaches pi over 2 from the left of the tangent function, not the inverse of the actual tangent function, is going to be positive infinity. Now remember, with inverses, we can switch the inputs and the outputs. So I can also say that the limit as x approaches infinity of the inverse tangent is going to be pi over 2. So I switched my inputs and my outputs using the idea of the inverse. I can do the same thing if I find the limit as x approaches negative infinity of inverse tangent. I can say that I know that the limit as x approaches pi over 2 from the right of tangent is negative infinity. So when I use the idea of the inverse, I can swap the input and the output, and I can say the limit as x goes to negative infinity of inverse tangent is negative pi over 2. In this next example, we're going to look at limits at infinity for power functions. And so this requires us to remember some of our graph shifting rules and our basic mother functions. So if I look at this function, f of x is equal to negative 5x to the third, we know that x to the third, we're just looking at the basic shape. We're not going to graph this perfectly. We know that x to the third has a shape that looks something like this. This is x to the third. And then we also know that that 5 in front gives it a vertical stretch, which means it's going to go up and down faster. It's going to make it grow faster by a factor of 5. So this is just a sketch of the graph of 5x to the third. Then when we graph negative 5x to the third and we throw that negative in the mix, remember that that negative is telling us that it's going to be a reflection across the x-axis. So then this graph of 5x to the third gets flipped, so now it looks something like this. So this is the final graph of negative 5x to the third. So now looking at that graph, this is our final graph that we're looking at. I can identify the limit as x goes to positive infinity of negative 5x to the third, and I can identify the limit as x goes to negative infinity of negative 5x to the third. As x goes all the way to the right, if I trace this graph using yellow going all the way to the right, my value of y is going down, and it's going down without bounds. So that means my limit is going to be negative infinity. Now, if I trace it going to the left as x approaches negative infinity, my y value is growing without bound. The limit as x goes to negative infinity of negative 5x to the third is positive infinity. Okay, let's look at this next graph. We're going to do the same thing for 2x to the fourth. X to the fourth looks similar to x squared. It just jumps up faster. This is x to the fourth. And then 2x to the fourth means there's a vertical stretch by a factor of 2, which means it's going to even jump up faster, so it's going to be even skinnier. And so this is the graph we're going to use to find our limits. So if I want to find the limit as x approaches positive infinity of 2x to the fourth, I'm going to look at what happens as I trace the graph from left to right. What happens to y as x keeps going out further and further to the right. So y is growing without bound, which means it's going to positive infinity. The limit as x goes to negative infinity of 2x to the fourth is going to be the same thing, because as I go left, as x goes to negative infinity to the left, y is growing without bound. In these three examples, A, B, and C, we're going to look at finding the end behavior of rational functions. And we're going to use the idea that the limit as x approaches positive or negative infinity of some fraction that has an x in the denominator and a constant on the top, that this is going to be 0. Because as that denominator gets bigger and bigger, whether it goes to negative infinity or positive infinity, that whole fraction is going to get smaller and smaller and smaller, and so the limit will be 0. And so we're going to use that idea when we find the end behavior of rational functions when we take the limit. So to find the end behavior of a rational function, we're going to take the limit as x approaches negative or positive infinity, right? As x goes all the way to the right and as x goes all the way to the left. What happens to the function? So we're going to take the limit as x goes to positive and negative infinity of 3x minus 1 over 2x plus 5. Now, the algebraic trick to this is to look at all the x's in the expression. So we have an x here and we have an x here. Now, when we look at that x, we're going to find the x that has the largest exponent, and whatever that is, we're going to divide every single term by the x that has the largest exponent. Since x to the first here is the largest exponent, I'm going to divide everything by x. So I have 3x divided by x, that leaves me with 3. Then I have 1 divided by x. Then I have 2x divided by x, that leaves me with a 2. And then I have plus 5 over x. When I find the limit as x goes to infinity, if you notice, everything is either a constant or has an x in the denominator. So when I take the limit as x goes to infinity, this limit is 0. This limit is 0. And I'm left with 3 halves, because on the top I have 3 minus 0, and on the bottom I have 2 plus 0. Now, if you think back to college algebra, we had rules about this. We didn't quite understand why it worked at that point, but we gave you that rule. And the rule was, for horizontal asymptotes, if the degree in the numerator is equal to the degree in the denominator, then the horizontal asymptote was going to be y equals, and then you take the leading coefficient of the numerator and divide it by the leading coefficient of the denominator. And in this case, if you look at the function, the leading coefficient of the numerator is 3, and the leading coefficient of the denominator is 2. So my horizontal asymptote is going to be 3 halves, which is exactly what we got here. Now, when you look at the graph of this function, you're going to get a picture that looks like this. And you're going to have a horizontal asymptote at y equals 3 halves. For part B, we have another rational function, and we are going to apply the same trick. We need to take the limit as x goes to positive and minus infinity of the function 3x squared plus 2x all over 4x to the third minus 5x plus 7. Now, we want to look to find all the x's in this expression. We have an x here, we have an x here, and we have an x here. Out of all those x's, x to the third has the largest exponent. So I'm going to take every single term and divide by x to the third. So when I take 3x squared and I divide by x to the third, I'm going to get 3 over x. When I take 2x and I divide by x to the third, I'm going to get 2 over x squared. When I take 4x to the third and I divide by x to the third, I get 4. When I divide 5x by x to the third, I'm going to get 5 over x squared. And then when I take 7 and divide by x to the third, I get 7 over x to the third. What happens is, as x goes to infinity, whether it's plus or minus, that whole fraction gets smaller and smaller and smaller until it approaches 0. So the limit of this would be 0. This would be 0. This would go to 0, and this would go to 0. So what's left is I would have 0 plus 0 on the top over 4 minus 0 plus 0, and that would give me 0, which means there's a horizontal asymptote at y equals 0, because when you look out all the way to the right, as x goes to positive infinity, and as you go all the way out to the left, as x goes to negative infinity, that end behavior is going to get closer and closer and closer to 0. If we graph this on our graphing calculator, we're going to get just a quick sketch. We're going to get something that looks like this. So if I trace this going out to the right, as x approaches positive infinity, I get closer and closer to the x-axis, which is y equals 0. And if I trace this going to the left, as x goes to negative infinity, that value of y is going to get closer and closer to 0. Now remember, the rule when we were in college algebra, the rule was if the degree of the numerator is smaller than the degree of the denominator, then the horizontal asymptote is going to be y is equal to 0. And this is exactly why, because if I divide everything by the highest exponent of x, what's going to happen is you're going to end up with 0 on the top over some number, some constant, which is going to end up giving you 0. For our next example, part C, we have the function 3x squared plus 4x over x plus 2. So we're going to try to use the same technique to find any end behavior with this function. So I'm going to take the limit as x approaches positive or negative infinity of 3x squared plus 4x all over x plus 2. Now, if you notice, here's all my x's, and my largest exponent for x is 2. So I'm going to try to divide everything by x squared. So when I take 3x squared and divide it by x squared, I'm left with 3. And then when I take 4x and divide by x squared, that gives me 4 over x. When I take x and divide by x squared, that gives me 1 over x. And then when I take 2 and divide by x squared, I get 2 over x squared. Okay, now, when we start plugging in really large numbers, x goes to positive or negative infinity, these values here are all going to approach 0. Because when the denominator gets really, really big, whether it's negative or positive direction, those fractions get smaller and smaller and smaller. So they get so small, they go to 0. But now look what happens. Now I'm taking the limit as x approaches positive or negative infinity of, what I'm left with is 3 plus 0 on the top, which is 3, over 0 plus 0, which is 0 in the denominator. And so this does not work. This technique does not work for this particular rational function. And if you notice, here's why. Because the degree in the numerator is bigger than the degree in the denominator. And instead of having a horizontal asymptote where the graph flattens out on either end and approaches some particular y value, it's going to have what's called a slant asymptote. So we have to use a different technique here. You're going to divide by the x with the largest exponent that's in the denominator. So if I have the limit as x approaches positive infinity, and I divide by the x with the largest exponent in the denominator, that would be x. So I'm going to divide everything by x. So when I take 3x squared and divide by x, that leaves me with 3x. When I take 4x and divide by x, that leaves me with 4. When I take x and divide by x, I get 1. And when I divide 2 by x, I get 2 over x. So now what happens is when I plug in positive large numbers, because I'm doing as x goes to positive infinity, this goes to 0, which means the denominator is going to approach 1, because I have 1 plus 0 in the denominator. And then what's going to happen on the top, as I plug in really, really large numbers for x, that numerator is going to get bigger and bigger, and it's going to go to infinity. So I have the limit as x goes to infinity of this rational function is going to be infinity. Now going in the other direction, if I look at the limit as x approaches negative infinity, we're going to get the same expression because I'm going to divide everything by x. So I'm going to end up with 3x plus 4 over 1 plus 2 over x. And when I plug in numbers that are really, really big that have a negative sign in front of it because we're approaching negative infinity, this approaches 0. So the denominator approaches 1. And then in the numerator, if I'm plugging in really, really big numbers, but I have a negative in front of those big numbers, then the top is going to approach negative infinity. So the whole function, as x approaches negative infinity, is going to approach negative infinity. Now, when we look at the graph of this function, I'll just do a really quick sketch. This is not accurate by any means. Just going to look something like this. I'm supposed to have a vertical asymptote here and a slant asymptote here, so it might be easier for me to draw the asymptotes first so I can get the shape a little bit better. So as I trace this graph and I head in the positive direction on the x-axis, and I'm going to positive infinity, my y value is increasing without bound, so my limit is going to be infinity. Now if I trace the graph going to the left as x goes to negative infinity, this is decreasing without bound, so that means my limit as x approaches negative infinity is going to be negative infinity as well. Now, if we think back to our rules in college algebra, remember, there were 3 rules. We already covered 2 of them. There was one rule that said if the degree in the numerator is the same as the degree in the denominator, then you take the leading coefficient of the top and the leading coefficient of the bottom, and you divide them, and that's going to give you your horizontal asymptote. Then the next rule was if the degree of the top was smaller of the degree of the bottom function, then no matter what, the horizontal asymptote was going to be y equals 0. Then the last rule said if the degree of the top is bigger by 1, then there is no horizontal asymptote. We have a slant asymptote instead. So now you can see where these rules are coming from. So we use these rules in college algebra, but now you can see where they're coming from. Okay, in this example, we're going to see how to determine end behavior for a function that has a radical in the denominator. Now, this is a little bit tricky because you have to really take into consideration the difference between dividing something under the square root versus not under the square root. So we're going to take the limit as x goes to positive infinity of 3x minus 2 over the square root of 4x squared plus 5. Now, here's the trick with this. I'm going to multiply the top and the bottom of this fraction by 1 over the absolute value of x. And the reason why I'm using the absolute value of x is, number one, we have to make sure that we are dealing with positive numbers under the root. So we want to be able to pull that x on the inside of the square root as an x squared, so I can get rid of that x squared with the 4. So like we did before, we tried to find the highest exponent of x, and then we divided all the terms by that x with the highest exponent to try to simplify it in a way that we can take the limit as x goes to infinity. However, when you're dealing with the square root, you have to remember that when you want to get rid of an x squared that's under the square root, on the outside of that square root, it's represented as an x. And it's going to be a positive x, so we're going to take the absolute value of x. And that's because the square root of x squared is the absolute value of x. When it comes out of the square root, it's x, and it's definitely got to be positive. We're going to take the limit as x goes to infinity. Now I'm going to multiply through, so I have 3x over the absolute value of x minus 2 over the absolute value of x all over the square root. Now when I bring the x on the inside of the square root, it comes inside as an x squared. So I'm going to have 4x squared divided by x squared, which is 4. And then I have 5 divided by x squared, which is 5 over x squared. Since we're finding the values as x goes to positive infinity, we're looking at all the really, really big positive values. So I don't really need to worry about the absolute value in the numerator anymore. So I have 3x over an x that's positive. Since I know x in this case is going to be positive because we're doing it as x goes to positive infinity, I can cancel those x's out and I'm left with 3. Same thing with the x under the 2. I can rewrite it as 2 over x because I know for sure that x is going to be positive. And then in the denominator, I have 4 plus 5 over x squared. As I look at the limit as x goes to positive infinity, as the x's get really, really big, this is going to get close to 0. This is going to go to 0. And then what you're left with is 3 over the square root of 4, which is 3/2. So the limit as x goes to positive infinity of this function is going to be 3/2. Now let's do it from the other side. I'm going to take the limit as x goes to negative infinity of 3x minus 2 over the square root of 4x squared plus 5. And I'm going to use the same trick. So now when I take the limit as x approaches negative infinity, after I multiply through, I'm going to have 3x over the absolute value of x minus 2 over the absolute value of x all over the square root. Now when I bring that absolute value of x inside the square root, it comes inside as an x squared because outside it's the absolute value of x. Now when I think about plugging in numbers that are really, really big but in the negative direction, I'm going to be plugging negative numbers. So if I plug in a negative value here and then a negative value here, when I take the absolute value in the denominator, that becomes positive, And then I end up with a negative over positive, so I'll end up with a -3. This is going to approach 0. This is going to approach 0. And I'm going to be left with -3 minus 0 over the square root of 4, which is 2. And so for this limit, I'm going to get -3/2. Now, if you look at the graph of this on your calculator, let's see if I can draw this. Sorry, it's kind of smushed down here. You're going to have a picture that kind of looks like this, and you're probably better off checking it on your graphing calculator because I have horrible art skills. It's going to look something like this, where you have a horizontal asymptote at +3/2, and then you have a horizontal asymptote at -3/2. So when you trace the graph approaching positive infinity, you're getting closer and closer to the value of 3/2 for y, and then going to negative infinity, you're getting closer and closer to -3/2 for y. In this example, we're going to look at a function that involves the natural exponential function, and we're going to look at the end behavior. So the first limit, we'll do x to positive infinity, and we'll do 2 plus 3e to the x over 7 minus 5e to the x. Now, if we start thinking about plugging in really large numbers in for x, e to the x is going to get really, really big. And we're going to end up with infinity over infinity for this fraction. So what we're going to do is we're going to use that same trick we did in the previous examples. We're going to divide everything by e to the x. So I'm going to have 2 over e to the x plus 3 e to the x over e to the x just leaves me with 3. And then I have 7 over e to the x. And then 5e to the x divided by e to the x is just -5. Now, when I plug in really big numbers now in the denominator under the 2, e to the x is going to start getting really, really big, right? If I plug in e to 100, e to 1,000,000, e to 2,000,000. As that x gets bigger and bigger and bigger, the denominator gets bigger and bigger and bigger. So the whole fraction gets smaller and smaller and smaller, where this goes to 0 and this goes to 0. So the limit as x goes to infinity ends up being -3/5. So now let's take the limit as x goes to negative infinity. And we're going to do 2 plus 3e to the x over 7 minus 5e to the x. Now with this one, since we are plugging in values for x that are really, really big that are negative, what we can do is we can rewrite this, the limit as x goes to negative infinity of 2 plus 3 over e to the negative x. Remember, you can change the sign of the exponent if you take the reciprocal. I'm going to do the same thing down here. This is a nice little trick. So I'm going to flip the e to the x upside down, take the reciprocal, and make the exponent negative. Now the reason why I did that is now think about what values of x we're plugging in to find the limit. As we take the limit as x goes to negative infinity, we're taking and plugging in really, really, really big numbers, but negative numbers. So when I plug those numbers in for x, I get a negative number, which turns positive. And so I get a really, really big value in the denominator. And as that number in the denominator gets bigger and bigger and bigger, the whole fraction gets smaller and smaller and smaller. And the same thing goes for down here. So now I'm left with the limit as x goes to negative infinity is 2/7. So you have to be really good with your algebra skills and think about these tricks on how you can manipulate these expressions, and think about the values that you're plugging in as x approaches whatever value it is that you're looking for, so that you can figure out how to handle these algebra manipulations. What can I do to make this work for me? In the next few examples, we are going to put all of these features together that we've learned about end behavior, local maxes and mins, concave up, concave down, all that stuff. And we are going to graph some functions. So I'm not going to read all these steps to you. You can read them yourself. But we're going to walk through these steps to find everything we need to graph. In this first example, we're going to graph a polynomial. So for step 1, we have to identify the domain. And because this is a polynomial, we know that there's no holes or jumps or asymptotes or anything goofy going on with this function. So we can say that it is defined over all the real numbers. So we can say the domain is from minus infinity to positive infinity. Now we're going to find the intercepts. The y-intercept is the value of y when x is 0. So when I plug in 0 for x into the function, I'm going to get 2. So my y-intercept is 0, 2. My x-intercept, we're going to have to set y equal to 0 and solve for x. Since this is factored, it makes it a lot easier. So I have 0 is equal to x minus 1 squared times x plus 2. So I'm going to have two x-intercepts at 1, 0, and negative 2, 0. Step 3, we're going to evaluate the end behavior. So we need to find the limit as x goes to positive infinity and x goes to negative infinity. So as I pick it really, really large numbers of x that are positive, like say 1,000,000 or 2,000,000, as I plug those values in for x, they're going to be growing without bound. So I can say that the limit as x approaches infinity of our function is infinity. Now, if I look at the limit as x goes to negative infinity, if I start thinking about plugging in really, really big numbers, but that are negative, that first factor that's squared, if I plug in really large negative numbers there, that squared is going to make it become positive. And then when I plug in really, really large numbers into the second factor, that's going to stay negative. So then when I take a positive times a negative, that's going to be a really, really, really large negative number. So I can say that the limit as x goes to negative infinity of our function is going to decrease without bound. So it's going to go to minus infinity. Since f is a polynomial function, we don't have to worry about any asymptotes. For step 5, we want to find the derivative and find the critical values. So here's our function. Now I have to use the product rule and the chain rule here. So think of this is my function g and this is my function h. I want to find the derivative by taking the derivative of g times h plus the derivative of h times g. So when I take the derivative of g, I get 2 times x minus 1, and then I take that 2 and bring it down by 1, so it's to the first, and then I multiply by the derivative of the inner function, which is just 1. And then I have to multiply that by h, which is x plus 2. Now I have to take the derivative of h, which is just 1, times g, which is x minus 1 squared. Now, after we clean this up and we distribute and combine like terms, we're going to get the derivative as 3x squared minus 3. So, to find our critical values, we're looking to see where the derivative is 0 or where it's undefined. Because the derivative itself is a polynomial, we're not going to have any values that make the derivative undefined, but we can see what makes the derivative 0. If I factor this, I can divide both sides of the equation by 3, and so I'll be left with x squared minus 1. And then the x squared minus 1 can be factored into x minus 1, x plus 1, which means our critical values are going to be plus or minus 1. So when I put that in a sign chart, I got -1 and I got +1. And I'm going to pick test points. On this first interval, I'll pick x is -2, and I'll pick x is 0. And then for the last interval, I'll pick x is 2. Now, when I plug in -2 into the derivative, I'm going to get a positive value, which means it's increasing on that interval. When I plug in x is equal to 0, I'm going to get a negative value, which means it's decreasing on that interval. When I plug in +2 into the derivative, I'm going to get a positive value, which means it's increasing on that interval. Now we know the places where the function is increasing or decreasing. Let's look at step 6. We're going to find the second derivative, and the second derivative is going to be 6x. So I'm going to have a point of inflection at x equals 0 because that's what makes the second derivative 0. And when I make my sign chart, if I plug in my test points, if I plug in x is -1 for the left interval and x is +1 for the right interval, when I plug in -1 into the second derivative, I'm going to get a negative value, which means it's concave down. And when I take 1 and plug it into the second derivative, I get a positive value, which means on that interval, it's concave up. Now we can put all of this together. I'm going to have to use the next page because I'm running out of space here. When we put all this together, we have an x-intercept at -2. We have an x-intercept at +1. We have a y-intercept at +2. We know that since -1, at the point -1, it's increasing and then decreasing. If we look at the sign chart for the first derivative, since at -1 it's increasing and then decreasing, we know that that's going to be a max at -1. And then we know that since it's decreasing and then increasing, we know at +1 it's going to be a local min. We also know that it's concave down from -infinity up to 0, and then it's concave up from 0 to infinity. So when we put all that together, we can picture what this graph looks like. So concave down would look something like this. With a maximum at -1, and it comes back down here, and then it turns to concave up with the local min at x equals 1. And so here we have concave down on this interval. We have concave up on this interval. We have our point of inflection at 0, 2. And we have a local max at -1 and a local min at +1. The next example, we are going to graph a rational function. So step 1, we need to look at the domain. And the domain is defined where the denominator is not 0 in this case. So whatever we plug in for x, and that makes the denominator 0 is going to be values that are not in the domain. And so plus or minus 1, if we plug that in for x, we're going to get 0 in the domain. So the domain is going to be all real numbers except plus or minus 1. So we're going to write that the domain minus infinity up to -1, not including -1, union -1 to 1, then union 1 to infinity. So basically we're going from negative infinity to positive infinity, but we're creating the intervals so that we skip over 1 and -1. Okay, step 2 is we find intercepts. So for the y-intercept, that's the value of y when I plug in x is 0. So when I plug in 0 as x, I get that the y-intercept is 0. And then because it's the special case where it crosses at the origin, the x-intercept is also going to be 0, 0. Now for step 3, we're going to find the end behavior. So let's do the limit as x approaches plus or minus infinity of x squared over 1 minus x squared. Let's try to use the trick where we divide every term by the x term with the highest exponent. So I'm going to divide everything by x squared. So that gives me a 1 in the numerator because x squared divided by x squared is 1. Then when I take the 1 in the denominator and divide by x squared, I get 1 over x squared. And then when I take x squared divided by x squared again, I get 1. So this is going to go to 0 because the numbers in the denominator are going to get really, really big. So the whole fraction is going to go to 0. And then what we're going to be left with is 1 over -1, which is -1. And that tells us that we have a horizontal asymptote at y is equal to -1. So as x goes way out to the left and way out to the right, the function is going to start to level off at y is equal to -1. Okay, step 4, we're going to try to figure out if there's any vertical asymptotes. And we can see that there's definitely going to be some vertical asymptotes that happen at plus or minus 1, but what we need to do is figure out the direction that they're going. Is the function coming to the right or to the left of the asymptote going to positive infinity or negative infinity? So I'm going to take the limit as x approaches 1 from the right of x squared over 1 minus x squared. And if I'm coming 1 from the right, that means I'm picking numbers that are bigger than 1. So in the denominator, I'm going to have 1 minus some number bigger than 1, which means that I'm going to get a negative value in the denominator and a positive value in the numerator, which is going to make that go to negative infinity. Now, if I do numbers coming from the left of 1, that means I'm plugging in numbers that are close to 1 but less than 1. And so if it's less than 1, that denominator is going to be positive, and the numerator will be positive, which means it's going to go to positive infinity. So that's what's going to happen to the left and to the right of the vertical asymptote at x equals 1. Let's see what happens at the vertical asymptote at x equals -1. We're going to do the same thing. The limit as x approaches -1 from the right of x squared over 1 minus x squared. If I plug in numbers that are to the right of -1, that means we're plugging in numbers that are like -0.9, -0.99. So those, when I plug those values in, I'm going to get a positive value in the denominator, and that's also a positive value in the numerator. And so overall, that's going to give me positive, a big number that's positive, so that means it's going to positive infinity. Now let's look at numbers that are coming from the left of -1. If I plug in numbers on the left of -1 that are close to -1, we're talking about like -1.1, -1.2. So if I plug in numbers that are close to -1, then I'm going to get a negative in the denominator and a positive in the numerator, which means the numbers are going to get really, really big fast, but they're going to be negative. Step 5, we need to find the critical value, so I have to take the derivative. So this I have to use the quotient rule. For lack of space, I'm going to let you do some scratch work and find the derivative using the quotient rule. And then you check to make sure you get the same thing that I get. But when I take the first derivative, I'm going to get 2x over 1 minus x squared, all squared in the denominator. So my critical values is where the derivative is 0 or where it's undefined. So when I set up my sign chart, if I look where it's undefined, I'm going to have plus or minus 1. If I look to see where it's 0, if I plug in 0 for x, that would give me 0 for the derivative. So 0 is also a critical value. So that's the values that I'm going to plug in on my sign chart. Now for my test points, I'll pick, let's say I'll pick -2 on that interval. Let's say -0.5 on that interval. Let's say +0.5 and then +2. Now, when I plug in these values into the derivative, I'm going to get that on this interval it's negative, so that's decreasing. On this interval, it's also negative, so that's decreasing. And then I'm going to get the interval is increasing and then increasing. So it looks like the only local max or min that we have is at 0 because it's decreasing and then increasing. So we're going to have a local min at x equals 0. Okay, now let's do the second derivative. Again, for the same reason, I'm going to let you guys do this on some scratch work and check your answer with me because I'm running out of room. When you take the second derivative, you should get 6x squared plus 2 all over 1 minus x squared cubed. Now, what makes the second derivative 0 or undefined? Oh, for this one, we're only going to have plus or minus 1. Now, for test points, let's use -2, 0, and 2. Now, when I plug in my test points, I'm going to get that this is negative, which means on this interval it's concave down. I'm going to get, when I plug in 0 into the second derivative, I'm going to get that it's positive, so it's concave up. And then on the last interval, I'm going to get a negative number, which means it's concave down. Now, when we put this all together, we've got vertical asymptotes at x equals -1 and x equals +1. We got a local min at 0. And based on the asymptote information that we got with the limits coming from the left and from the right, I know that it's going to go up like this, just a sketch. I'm a terrible artist. We also know that we have a horizontal asymptote at -1. So it's going to flatten out there. So this is what our final graph is going to look like, just a sketch. In this last example, we're going to graph a function that has a cusp. We're going to find the domain, and since x minus 1 raised to the 2/3 is the same thing as the cubed root of x minus 1 squared, we don't need to worry about having negatives under the root because this is going to square anything that we put in there. And then also we don't need to worry about negatives under odd roots. So this is going to be all real numbers for this domain. Step 2, we're going to find the intercepts. So first, let's find the y-intercept. And so we're going to do that by plugging in 0 for x and see what we get out for y. And when we do that, we get that the y-intercept is 0, 1. Now for the x-intercept, we need to see what makes the function 0. So we're going to set the function equal to 0, and then we'll get that x is 1. So our x-intercept is going to be 1, 0. For step 3, we are going to look at the end behavior. So we're going to take the limit as x goes to positive and minus infinity of the function. And as you plug in really, really, really large positive numbers, then the whole function is going to grow without bound. When you plug in negative numbers, because you're squaring it, you're still going to get out positive numbers, so it's going to grow without bound as well. So whether you plug in positive or negative numbers, it's going to grow without bound. So my limit as x goes to positive or minus infinity is going to be infinity. Now, for step 4, we need to look for vertical asymptotes, and because we don't have any denominators here, where we have to look to see where the denominator is equal to 0, we're going to get no vertical asymptotes. Step 5, we need to find where the function is increasing and decreasing, so we're going to take the first derivative. When we take the first derivative, we're going to get 2 over 3 times x minus 1, all raised to the 1/3. Now you guys can do some scratch work off to the side. Just make sure you get the same thing that I get. Our critical values are going to occur when the derivative is undefined or where the derivative is 0. So when we look at that, it's undefined when x is equal to 1. It's impossible for that derivative to be 0, but it can be undefined when x is 1. So we're going to put 1 on a sign chart, and we're going to do test points. So if I use the test point 0 on the left side and like say 2 on the right side, and I plug those numbers into the derivative, I'm going to get negative on this interval, which means it's decreasing. And then when I plug in 2 into the derivative, I get positive, which means it's increasing. And that also tells me if it's decreasing and then it's increasing, that x equals 1 is going to be a local min. The other thing, though, is because when the derivative is undefined, remember that's where we have a point or a cusp. So this is going to be a local min, but it's going to be at a point or a cusp. Okay, number 6, we're going to use the second derivative to find where it's concave up and concave down. So when I take the second derivative, do some scratch work and check to make sure you get the same thing that I get. I'm going to get that the second derivative is negative 2 over 9 times x minus 1 raised to the 4/3. And again, the second derivative can't be 0, but at x equals 1, it's undefined. So we're going to put 1 on our chart, and we're going to pick test points again. I'll use the same points, 0 and 2. Now, when I plug in 0, I'm going to get that it's negative, so that means it's concave down. And then when I plug in 2, I'm also going to get a negative value, which also means it's concave down. So most of the graph is going to be concave down except for that point at x equals 1. So now when we put this all together, at x equals 1, we know there's a local minimum. We also know there's going to be a point or a cusp. If it was coming to a point, my lines would be straight. Since it's concave down on minus infinity up to 1, and then from 1 to positive infinity, I know it's going to probably look something like this. And let's see, it says we also got that the Y-intercept was at positive 1, so we know that it crosses right here at the point 0, 1. So this is just a rough sketch of our function of x minus 1 all raised to the 2/3.